You are listening to NASA in Silicon Valley, episode 68. Frank, tell us about our guest today.
Hey, Matt. Today we're talking with Kevin Sato, the project scientist and deputy project manager of NASA's space biology research projects. So space biology is basically figuring out how humans can live in space, on Mars, on the moon, wherever we end up going. And Kevin not only works on some of these individual experiments, but also looks at the big picture of developing a portfolio, picking what experiments go when, and basically planning all of that out for the future.
And all this is very relevant now as we're getting ready for towards the end of this month for SpaceX 13, where we'll be launching up to the International Space Station, of which there'll be several Ames payloads in science experiments.
Yeah, definitely. And rodent research is something that Kevin's worked on in the past, and Rodent Research 6 is one of the science experiments that will be going up to the space station again looking at, how life changes when it's put into space.
So on a similar note, we are a NASA podcast, but we are not the only NASA podcast, and our friends over at the Johnson Space Center have a podcast called Houston, We Have a Podcast. We're actually, as a special treat, going to be doing a joint episode with those guys next week, where we'll be talking about SpaceX 13 and some of this work.
And the really exciting thing about that is we'll actually have an astronaut calling in, so we'll be able to get two ends of the spectrum, both the astronauts that are on the space station actually doing these experiments, and some of the scientists that are, developing those experiments, so we're getting both perspectives.
And so as a special shout out, also from NASA's headquarters, they're going to be launching a new podcast this very week called Gravity Assist that is going to be run by our director of planetary science, the famous Dr. Jim Green. He's basically giving a virtual tour of the solar system and beyond, starting on with the sun, building all the way up into 10 episodes that'll end in Pluto. But before we just jump into our episode, a reminder, we have a phone number. This is 650-604-1400. Any questions, comments, go ahead and give us a call and leave a message for us, and we can figure out how we'll add that into the podcast. But for those who want to be on social media, we are using the hashtag NASA Silicon Valley. But for today,
let's hear from Kevin Sato.
we always started off the same. Tell us a little bit about yourself. What brought you to, how did you join NASA? How did you end up in Silicon Valley?
Well, actually, I didn't end up in Silicon Valley. I grew up in the Silicon Valley. I grew up
happens.
I grew up in Mountain View.
Really?
Went to Castro Elementary School, Graham Middle School, and Los Altos High School. So I know this area and I know this base.
And that's so rare in this area with having the Google headquarters next door, Facebook headquarters. It's like this big tech boom in this area. It's kind of rare you find people who are natives.
Oh, yeah. No, I remember when the Bay Area was actually a large number of orchards.
Yeah.
And the actual part related to the silicon part, the semiconductor industry was just getting started. And so it's been really kind of a treat to see how the Bay Area has grown up from one type of technology through to the next generation.
Well, a while back we had an episode with Jack Boyd where he was telling about the history of the place. And I know a big part about putting an NACA, now NASA, center in this area was also taking advantage of, you have Stanford, you have all these universities, you have all, companies. It's like, this is just like a very fertile ground. So I'd imagine growing up in this area, it's like just seemed such a natural flow to end up working over in NASA.
Yeah, it is. I was lucky enough to be, or old enough to actually be able to remember back to Apollo. In fact, one of the first things I remember about NASA was being at my grandmother's house one Sunday for dinner, and we all went outside, and my dad and uncle somehow knew Gemini.
Really?
Don't remember which mission was actually going to fly over. And so we looked up and we saw Gemini come right over. So that was the first thing. But I remember all the Apollo missions. But actually my coming to work for NASA, which is something I thought would never, ever happen, was actually very accidental. I was completing my postdoctoral fellowship, and there was an opening that I was called in for to actually work with the NASA Flight Payloads Group at that time. And so it was a complete shift, and where I would no longer be doing research, but actually working with principal investigators to translate their dreams and their goals for their scientific research into ones that they can actually conduct into space to understand the usual. How does life respond to
Yeah.
space? But a lot of the scientists were also interested in not necessarily just exploration, but they were really interested in using the space environment to understand how a particular disease state occurred, and then turn that back into understanding how we might be able to solve that on Earth.
Well, I always get the kick out of, especially talking to anybody who's working on payloads, that mix of, science, research, scientific method, hypotheses, running experiments, but also the engineering side of building a thing that can survive a launch, that can get up into the space station and do this. But like in your own background, was it more science? Was it engineering, working on payloads, or is it both? Or how did that even launch into working at NASA?
So my background was straight science.
Okay.
It was straight fundamental research. I was focused in the areas of human cancer, human molecular biology, and the development of the cancer, and how cells divide. And so when it came to moving to the NASA side, it was very much no longer that specific area where you're focusing. You were really utilizing everything you had learned and as a scientist, because now you weren't just looking at one thing. You had to be able to understand the science in many different areas: Drosophila focus, cell, rodent, C. elegans, just microbiology, a lot of different areas. So it was really interesting because I was now pulling on all of my experience and education in order to work with the investigators. But the really interesting thing was the folks that I worked with, especially the engineers and the operational people, because they were very helpful in really learning what they did, but learning their language. Because I think something people don't think about is, it's science. You can talk science.
Yeah.
But in a lot of ways, when you move from one type of area of research or method into different areas, you're actually learning to speak differently. You're learning in a lot of ways a new language, a new way to communicate, and being able to say, here's what the science needs to engineer so they understand how to implement it. Here's what science needs so the operational folks need it. And then here's how we justify it so people in business, in management can understand what's needed. And so that's kind of been the interesting part about my career here, is that, you're forever growing and learning and learning new ways to communicate as I've been moving through the different areas that I've been involved in.
And so starting off, it was payloads, is like from the beginning, or helping people design those experiments?
Right. So it was science operations. Basically, there were a series of phases that we go through. And the first phase was taking an investigation, translating that into a flight-capable investigation for defining the requirements of that investigation. For example, a principal investigator wanted to be able to study how quail developed in space. Right. So now you have to say, okay, how do we translate that into a set of requirements that engineers can understand to develop the hardware they need? So you say, okay, well, the quail needed to get air of this amount. They need to be able to develop. Like with anything, the eggs need to be turned periodically.
Yeah.
They need a certain temperature. So you're looking at all of these particular perspectives of the investigation and turning it into, rather than I need to do this study like you would in a lab, to specific defined specifications that anyone can look at and go, okay, I know what you need so that I can run it operationally as well as engineering wise. And that was a real large difference, because you don't think in those terms necessarily as a scientist. You do subconsciously, but you never have to really put it down in paper and tell someone else.
Well, I imagine as a researcher, as a scientist, you have a lab, you probably have a little bit more freedom of like, okay, here's my hypothesis, this is what I'm looking at, design the experiment, run the experiment, control groups, you do the whole rigmarole. But like, there's only so much stuff that can go to the space station, and it takes a lot of effort and a lot of money to get something up on the space station. So I'd imagine it's as like, I don't know, I'm just making this up. You can tell me if I'm wrong. I'm thinking of like of a funnel of people propose a lot of ideas, a lot of investigations, a lot of theories, and then that slowly gets whittled down to, okay, what's an actual real experiment, and how can we actually like put it up? Is that kind of how it works to narrow down who wins and goes up to the space station? Yeah,
exactly. So the way it works is NASA puts out regular, what's called NASA research announcements.
Okay.
They're solicitations. And they go through, for flight investigations, they go through basically 3 series of reviews. The first one is a peer review. So scientists from the scientific community come in, They review all of the grants for scientific merit. Is it worth doing? Is it addressing a question that's worth asking? And is the science that is being conducted of high merit and worth us funding? Once those receive a passing score, they then get passed on to the different centers who have the expertise, and we look at them for now technical feasibility.
Okay.
Exactly as you said. Can you actually conduct this experiment in space? Can we actually turn this into a flight experiment within the constraints and the requirements and capabilities we have available? And then once they receive a score for that, it's combined with the main peer review score. And then we look at it at the headquarters levels in terms of programmatics and funding. Do we have the funding for how many can we support? Programmatically, does it actually fit what we're interested in and our objectives for exploration, standard fundamental knowledge advancement? Once all of those are considered, then the final winnowing goes down, as you said, to a funnel where a certain select few are then recommended to, in our case, the Space, Life, and Physical Sciences Research and Applications Director for his approval to fund those particular investigations. Once that's done, the principal investigators are notified. And then for us at the center, when I was doing flight payloads, the fun begins, because then we meet the PIs, we learn about what they're doing, and we now take the first steps to defining their experiment requirements in terms of flight investigation, and then we go from there.
In the role that you're working in even now, it's like you're not just working on one experiment and one thing. You're looking at a whole suite, or the whole of the program, all these different experiments and different things.
Yes. So now I'm working more on the programmatic side with the strategic and tactical planning, but also looking across our entire portfolio of investigations to identify which experiments we want to fly, in which priority orders, based on what we know is currently the programmatic needs, not just for NASA space biology, but also for the Human Research Project, possibly also with respect to commercial in other areas. But primarily, what do we need to understand and know in order to safely fly humans to the moon and to the Mars again? And so that's why I work across all the portfolios. And then we then hand those to the various implementation groups or our definition leads to begin that study. And I'm still doing definition work and working with PIs, but less so. And we have a group of people, really great people, who are portfolio leads and also our mission scientists, who are now the next generation of folks who are taking experiments out to space.
Yes. So early on in the podcast, it's like we spoke with David Smith, who's in the space bioscience group, and also Elizabeth Payne on some of the, working on like payloads and different things. So your day-to-day is working with these people, understanding these experiments, and kind of like getting them all lined up to become a reality. And I know one of the big competencies, one of the big things that Ames does is focusing on space biology. And so talk a little bit about that. I always hear I love the catchphrase of the International Space Station of working off the Earth for the Earth. So why is it important to have like a space, like a space biology or, space biosciences? What are we looking for? What are we trying to understand?
Right. So space biology is actually a very unique field of study. I think most people, when they think about research, you're doing it in gravity, you're doing it in 1G on Earth, and you're doing it in an environment that you can control, that basically life evolved in. Now, when you leave Earth, all of those sort of norms that you understand biology to function by, all of the norms that you do research by, change completely. For example, when you go into orbit, you're basically in free fall, you're in microgravity, and biology changes. You see changes where you no longer have the standard gradient of fluid pressure, for example, in the body from the head to the feet. All that begins to equalize out. Mechanical stimulations that you would get from walking or moving are reduced or eliminated. And so you need to start to think in terms of what is going on in the absence of the gravity. But also the science itself is also thinking about, if I'm going to conduct this research in space, why do I need to conduct it there? What can space flight, that environment, tell me that I cannot do on Earth? And there are a lot of things. For example, there are potential disease syndromes, such as, I think everyone understands, osteoporosis.
Okay. Yeah, like bone density. So.
Bone density, correct. And on Earth, that takes years and years, almost lifetime, to occur. Mm-hmm. To study that over someone's lifetime means that 80, 90 years before you get any understanding. However, it's known that when astronauts go into space, and we've seen this in rodents, there's an almost immediate start in loss of bone.
Oh, really?
Yes. And so the understanding is that there's somehow a disconnect between how bone is degraded and bone is formed. On Earth, there's a homeostasis, meaning there's a static change with how you lose bone and gain bone, because you remodel your bone throughout your life. Well, in spaceflight, as in osteoporosis, there's a disconnect between the bone loss and the stimuli to stimulate the cells that will come in and form bone. That's no longer there. Mm-hmm. And so you get more cumulative bone loss than you do bone formation. And that's what occurs to give an osteoporotic-like state in bones in astronauts and rodents. One of the questions that's out there is, does this particular state really describe what happens in the disease state on Earth? And there's a lot of indications that, yes, that's true. But it's an area that's of very high and strong research that we at Ames are actually very, very much involved in. Some of the scientists who are actually studying those areas and are finding major breakthroughs in how it might be occurring at a mechanistic level, and also how we may be able to identify some countermeasures that may stop that particular state.
Yeah, I think naturally when you think about like these biology experiments in space, there's like biology in space. Naturally, you tend to think of, going to Mars, humans going to the moon, living long term out in space, how that affects you. So there's a natural connect to that. But there's also a lot of, pharmaceutical industries. There's other things that you can learn that can help us living on Earth that aren't necessarily related towards the journey to Mars. But it's just things that you can learn about how microgravity affects biology that can help us out here.
Yeah, and that's key. I think a little while ago there was actually an NIH, a National Institutes of Health, call for research investigations that required the use of the spaceflight environment in order to address specific disease questions on Earth. And one of the investigators, who was one of the payload specialist astronauts years ago on the space shuttle and is studying aging, because there's a lot of aging analogs that occur, had identified that T cells, which are an important part of your immune system to activate cells that produce, the B cells that produce antibodies, weren't stimulated to become activated so they can do that work. Right, and so that was actually funded by the National Institutes of Health. There are companies who are actually using the space environment because of the acceleration in possible analog disease states in space in order to actually investigate possible countermeasure drugs that they can see whether it works or not. And based on that, they can either come back and say, hey, let's go look at this further. This compound looks like one that we might be able to use for further drug testing. Or the idea, I think, ultimately is the ability to maybe use the space environment to validate drugs. Now, that's a little harder because you have a limited number of specimens you can study. But I think the key is the fact that, as I mentioned with osteoporosis, there are certain physiological states in the human body or the animal or in other model organisms like Drosophila, C. elegans, and especially bacteria, where you're seeing changes occur at a much more rapid rate that you can actually analyze within a certain shorter period of time and get really good research data that you may be able to base some commercial basis for a drug, identification of a countermeasure or a potential therapeutic target.
Wow. So I remember the last time when we were hanging out and talking, I think we were talking about some of the rodent research stuff, and you're talking about how some of the new upcoming experiments of it's not only just hey, this is some of the stuff that NASA's working on to understand the journey to Mars, to understand how how this knowledge can benefit us on Earth, but it also going into how the teams are formatted and how the teams can work together and different things that you guys have learned about. So go ahead and talk a little bit about some of that stuff.
Everything we do here at NASA, which is, I think, one of the most exciting thing we do, is we work in teams, and we work in teams that have different specializations. We have scientists, we have people who know operations, and these are the guys that make things happen for us. For a scientist, we have engineers, we have people who are business project managers, we have PAO, education. We work in teams, and it's that interaction of the teams that make the science happen. So in the case of like the rodent research, there's a lot of different things that have to happen for a rodent research experiment. There's the identification of the science and what the requirements are that the scientists do, as well as working with our flight internal animal care and use committee in order to understand how we work with the animals to make sure it's done in a humane and ethical manner, because animals are very important for research. They always have been, and we look at them as partners in understanding in our trip to Mars. And once those are done, it gets handed off to our engineers and ops people to be able to then take that and translate it into an actual flight. What hardware do we need? What kits do we need to bring up in order to support the animals? What operational needs do we have in order to change out food, change out the water supply system, send them up, bring them back? But on top of that, where you see the integration of work within a project and within a specific flight, there's also the interplay that occurs between flights. Because as you're working on one investigation, you're starting to work on another, or you're finishing another.
It's just layered.
It's just layered, and it's like that for any investigations we do for flight payloads for any model organism. And that's one of the larger challenges, making sure that the teams are able to work in a manner where they can complete one and start another, or begin another while they're beginning to work and deal with one study that they're already doing. And so it's a very dynamic environment, and it's one in which it's very exciting because you're constantly learning something new, you're constantly doing something different, or you're constantly learning something you did the last time that you changed, and all of a sudden there's an improvement. But on the bottom line that I think we get as a team, and the greatest kick we get is when a scientific investigator comes back and says, hey, I can address all my objectives, specific aims. I can do my research, and I really want to thank you. And that's really rewarding, is because what you end up feeling, even though you're not doing the science, it's the fact that you've enabled something to occur that is going to benefit space exploration and potentially Earth and humans in general.
Well, and that's a really cool thing I enjoy about it, and thing that I've loved about talking with people during the podcast is also, it takes all different types to make this place run. Whether it's and it's also good because there's so many people who watched Star Wars as kids, or watched Space Camp or Star Trek, or people that are inspired by this stuff and they're love NASA, but maybe math's not their thing. Or maybe writing isn't their thing, or business classes. It's no matter what your area of interest is, there's a role to play. And it's when you take these smart people, and no matter what they're doing, no matter what their skill set or what they're working on, being science, engineering, technology, or if it's mission support, business cases, logistics, human resources, it all matches together, and by everybody working together, that synergy, you kind of come up with something greater than the sum of its parts.
Oh, absolutely. And the neat thing is that everyone is so excited about making things happen. I mean, these are folks that go over the top. They go beyond expectations because they know that the benefits to gain are great. And the other thing too that's neat is we don't just work within Ames and you fly. We're actually working with other centers. There are, the group at Johnson Space Center, Marshall Space Flight Center, Kennedy, Glenn. All of us are working together to fly a particular investigator or fly a series of experiments. And, one of the greatest thing is, you can talk to folks who you think, oh, they're so far away from what we're doing, but they're trying to help us. And they come back and say, so you're doing this, you need this, you have to have this. Or they're asking us questions that are actually stimulating us to think of, oh, I didn't think about that. And they understand it. And then when it goes to flight, I mean, they're right there. They're our advocates. They're fighting to get everything we need to get our experiments conducted in space and completed. And it's really amazing, when they talk about NASA as a family and NASA as a team, regardless of what center you're at. Everyone's working together for one goal, and that's to get exploration up. And that goal includes making sure that the science, the engineering, whatever we need to do is being accomplished at those levels to make that happen. And it's a really neat environment to see that it really is that large a family.
Excellent. So for folks who are listening to the podcast, anybody who has questions for Kevin, want to hit us up, we are on Twitter at NASA Ames. We're using the hashtag NASA Silicon Valley. So folks have questions, they can hit you up on Twitter and we'll get back to you and we'll go back and forth. But considering the work, for the space station, it's an ongoing thing. This isn't going to be the last time that we talk to you and your team. So but thanks so much for coming on over.
Well, thank you very much. I appreciate you giving me the opportunity to kind of talk a little about what I do and what we do as NASA on flight payloads to, help us get along with the exploration out to Mars and beyond the low Earth orbit.
Excellent. Talk to you later.
Thank you.